Today is the last video I'm going to be making for this, which is weird. It both feels like I've been doing this for a long time, and it doesn't feel like I've been doing this for a long time. It's been about, well, a little bit more than 2 months, and I don't know. It actually, it also doesn't feel like it's been 2 months, but I don't know. What do I know? Um, I guess let's just go ahead and do what we got to do. So, now we're getting into, well, the stuff that we've actually been doing over these last 2 months. First of which is the electricity unit. Now, for this, I've written out three different kind of questions, but really you can kind of combine the first two together a lot of the time because you can kind of get the same sort of things from that. So, um, let me kind of again show you the formula sheet for this, just so everyone knows. Again, it hasn't really changed here. So we have again K, the value for K. You have the charge of a proton and the charge of an electron. It's just that, but negative. Also, the mass of a proton and mass of an electron, if you need those for whatever reason. Here's the electric field strength, and then that the force is the new charge times the field. And if you somehow just have two charges by themselves, and you just want to find the force directly between them, you can kind of combine them to do that. Voltage you can get just from one charge, and then potential energy is a new charge times that voltage. And then also, if you just have two charges and want to find the potential energy between them, you can do that. The voltage and the potential energy is a scalar, the field and the force is a vector. And then you have all of your circuit rules. So V equals IR, and then the series sum for the resistance, the parallel sum for the resistance. And then you have, when it's in series, your voltages are summative and your currents are equal. And if they're in parallel, your voltages are equal and your currents are summative. Those are the rules we're going for to get for electricity. So let's start with a question that's again kind of combines the two at the top. So let me say, let me think. I'm just gonna make some stuff up here. Let's say, a +4 microcoulomb charge is 1.5 meters to the left of a +5 microcoulomb charge. You are standing 1 meter to the left of the +5 microcoulomb charge. Find the total electric field strength at your position. Okay, so we have two charges, a distance between them, and then we are standing between the two charges, and we're a certain distance from that as well. So, whenever we're finding a total electric field strength, you want to find what is this electric field caused by each of the other charges first. So we have E1, which we're going to deal with, and then later we'll deal with E2. So E1. So K is, again, always 9 to the 9. Q1, so that's going to, let's say the +4. So that's going to be 4 times 10 to the -6, since it's a microcoulomb. And then divided by R1. So this is going to be our distance from the +4 charge. Now I give you that you're 1 meter to the left of the +5 charge, and the total distance between them is 1.5 meters. So therefore, the distance from you to the +4 charge is going to be half a meter. Okay. So, on the top here, we have 9 times 4 is 36. And then 10 to the 9 times 10 to the -6 is going to be 10 to the 3. So that out there, that ends up being 3.6 times 10 to the 4. 0.5 squared is 0.25, which is the same as multiplying something by 4. So that would be, yeah. So this ends up being which ends up being simplified to... Yeah. I think that's right. Let me double check this because I did that without calculating anything in my... did that back in my head. So 9 times that divided by 0.25. 144,000, and that would be... Yep, that's right. Okay, so that is your charge from... I'm actually going to get rid of this just so I can switch direction. So this is your charge from the +4 charge. The +4 charge is on the left side, and it's a positive charge, and so remember the direction for the fields are outwards from a positive charge. We are to the right of the positive charge, so this is in the direction that's to the right. Okay, E2... So now we're going to be at 5 times 10 to the -6 divided by... yeah, so now we're just 1 meter to the left of the charge. Okay, so our distance is just 1. Okay, so now we're at 9 times 5 is going to be 45 times 10 to the 3, which ends up turning this into 4.5 times 10 to the 4 divided by 1. So that just gives you, well, 4.5 times 10 to the 4. Now this one, again, this one now, the charge is to our right, and again, it's still a positive charge, so since we are to the left of the positive charge, the field in this one is to the left. So, what is our total field? They're in opposite directions, they're going to subtract. So E total is going to be E1 minus E2. So we have... I'll just write this as full numbers. That is our 1 to the right minus our 1 to the left. So, well, I mean, I don't need a calculator for that because it's 9,000. Right? Whoop, no. No, it is that way. 99,000. Okay, whatever, I can't. I guess I do need a calculator. So that is our total field strength is to the right. The larger value is to the right, so it's this amount minus the smaller amount to the left, so the total is to the right. Okay. So a follow-up question to this would be, you have a, let's say, -2. What did I do? Okay, I pressed Shift and not Control. Or Alt. -2 microcoulomb charge at this position. What is the force that it feels? Okay, so for force, it's that you have a new charge times the field strength. So this new charge you're introducing is the -2 microcoulombs. Times the field strength we just got. So, if you multiply this out, so it's this times that 0.198. So that is our force. And since it's a negative charge, the field was to the right. When a negative charge interacts with the field, it goes in the opposite direction. So, this force is going to be to the left. So that's the idea with that. And for this, I mean, really the main thing is just I could make the configuration more annoying. Maybe I could even have it where it's like not in a straight line. I wouldn't make anything super terrible, but I would thinking I'm probably going to do something like that. So yeah, that'll be fun, I guess. Okay. Let's see. So I said an idea for a really evil problem. Okay, anyway, we'll see how that works when we get to the when I actually make the final, which I will be doing after I finish recording this. Okay, but you can sort of shift this now into another question where I can say same scenario, but now find the total, or actually wait, hold on. But actually no, but now find the total voltage instead. Okay, so same scenario, all the numbers are the same, but now we're finding the total voltage. And it's the same procedure where you have to find the individual voltages first, and then put them together to find what the total is. So, and let's again start with this. Is going to be the 4 times 10 to the negative 6 divided by, and now it's just r, not r squared. So again, it's 0.5. So numerator is the same. It's going to be 3.6 times 10 to the 4 divided by 0.5, which is the same as times 2. So this becomes 72, or 7.2 times 10 to the 4, which is 72,000. That's V1. V2. Not 90. That would change the universe a little bit. Okay, and then this is just going to be actually the exact same as the field, which is going to be 45,000 volts. So, here, again, what matters in terms of plus or minus is literally if you're having positive or negative charges. Both of these are positive charges, which means you're going to have a positive voltage for both, which means your total voltage is just V1 plus V2. So you have 72,000 plus 45,000, which is going to equal 117,000. Okay, you have a, and I'll keep this the same. Oh, I should say charge, but no, well. I'm lazy. What is the potential energy? Okay, so potential energy, and it's the new charge times the voltage. So our new charge is the 2 times 10 to the negative 6. Oh, it's minus, though. Well, so for energy, it doesn't really matter if it's plus or minus. Like, even if you had a negative voltage or something, whatever, energy is energy, right? So that will just kind of default to being positive. So 0.2. Oh, no, that doesn't make sense. Yeah. Joules. So yeah, even though it is, I mean, you say, oh, it should be negative. Yeah, but like, what does negative energy even mean? It doesn't really mean anything. So yeah, that's fine. Just leave it positive. So yeah, again, this stuff really just comes down to how annoying can I make the configuration of charges. For example, I could have 3 of them in a line, and then you have to worry about like all your distances between everything. Or again, maybe I'm definitely not gonna do something 3-dimensional, but I could do something 2-dimensional. I might do that. And I thought of a way to like really make that annoying. Well, I'll see what I'm thinking of. I have an idea, and I want to see how truly aggravating it is. But yeah. I mean, there isn't really much else I could show you for this. I could just give you different examples of different scenarios, but like it's the same math, right? It's just over and over. And again, we did a bunch of examples of this earlier, and you have the video for this when we went over this before the test for electricity. So, if anything, you should be pretty good at least of understanding the kind of stuff that I could ask you for regarding this stuff. Let's just kind of jump right into the circuit stuff. I actually did make a circuit. So here it is. Here's my circuit that I made. I just made this, so I have no idea what the numbers are here. So we're going to be solving this one together. So let's catalog what we have. There's 8 resistors, and they're numbered 1, 2, 3, 4, 5, 6, 7, 8. So let's figure this out. Okay, so you have R1 equals 1 ohm. I'll just label them this way to make it easy. Yeah, well, I'll just 5. I was trying to be fancy with the nomenclature, but screw it. Okay, and then I'll. We want to get I1. We want to get I2. Yeah, so we're going all the way. We're solving for the currents and everything. And also the individual voltages. Okay, now R6 is 6 ohms. R7 is 7 ohms. R8 is 8 ohms. And then I'll skip over here to make this stand out a little bit more. R total, we don't know. Oh, that's annoying. Okay, well, that works. No, wait. I6, we don't know. I7, we don't know. I8, we don't know. And I total, we don't know. And the total, we do know. It's 10. Okay. So those are what we have and what we want to solve for. So let's actually look at all of this. So, R6 and R5 are parallel with each other. So 1 over R5 6 equals 1 over R5 plus 1 over 6. Okay. Then R5 6 is in series with R7 and R8. So R5 6 7 8 is R5 6 plus R7 plus R8. Okay. R2 and R3 are in parallel with each other. Yeah, even though there's this sort of three-way thing here. Actually, wait, does that three-way make things difficult? I don't think so. I don't think that makes a difference. Or, no, I'm pretty sure it doesn't make a difference. Okay, I'm gonna assume it makes no difference. If it does, then we'll just have to redo this whole thing. So, I don't think it makes a difference though. So, the fact that there's a three-way connection, I'm pretty sure you can just treat it as that R2 and R3 are in parallel. Because if you think about, see, like for example, if I moved this to connect in with here instead, right? Then think about the current. The current would be this one flowing into here plus this current flowing into here, and you'd have both these currents coming in here. But then that current would just add to this current to get to this. So like the current is the same. It just behaves the same. It's all that's happening is that you have all three coming together at once instead of just these two coming together and then this one coming together, right? It's not like there's this other thing here that's happening. So I don't think it matters. Yeah, I don't think that matters. And then R also, especially because, and then I'm thinking, okay, well, how does that relate to this one? Well, the current that goes up here has to go through R4, and then it splits between 2 and 3. It's not like the one that goes through R4 then like switches to over here. So like I don't think that. Yeah. So then you would say that R234 is just R23 plus R4. Those are in series, and then. But then you could say that 234 is in parallel with 5, 6, 7, 8. I'm pretty sure you can just say that. So They got figures there. And then our total is just that you have R1 stuck on the end there. Like that. Okay, so let's copy this. So we have this here for reference. So let's kind of work our way up. So R5 and R6. R5, well, that's 5, and R6 is 6. So 1/5 plus 1/6 is it's not great actually. 6/30ths plus 5/60ths equals, or wait, 30ths, not 60ths. 11. I have a feeling these are going to not be great numbers because I just made these numbers on the spot, right? So that circuit 10 from that worksheet, that was, designed to be not as terrible as it could have been in terms of the fractions, right? So it's there for, oh, it's 11ths. Ew, okay. So R5/6 equals 30/11ths. Barf, okay. So 30/11ths plus 7 plus 8. We have 30/11ths plus 77/11ths plus 88/11ths. 95/11ths. Great, okay. Okay, so we're keeping that there. And then so we have here, then we have 1/2, 1/3. So that's 3/6 plus 2/6, so that's 5/6, which means R2, 3 equals 6/5. So we have then 6/5 plus 4. 4 is 20/5. So this is 26/5, not 56, 26. Which means we have 1/26/5 would be 5. Oh no. 5/26 plus 1/11. Oh god, okay. Ew. That's terrible. Do I want to keep this as a fraction? Sure, why not? Great. 195 times 5. So that's, wait, okay, 195 times 26. Denominator's 50/70. This is what happens when you make a question that, like, you're just like, oh, no, pick these numbers, and it turns out to be terrible. Okay, so it's 975 5,070ths plus 26 times 11, 286. Okay, so 1, 2, 1. Okay, wait, 1261 or 1? Yeah, 1261 70ths, which means, okay, so that's one. That's 1 over this, by the way. So that means the actual answer here is 50/70 1 over 12161 plus 1, which means it's 1261 over 1261 plus 50/70 over 1261, which equals 1261 plus 50/70 6331 divided by 1261. That's horrible. Does that simplify in any way? Doesn't look like it. Here, wait. I wanna factor it. Okay, hold on. No, they don't divide by 3. I don't know the 7 rule. I'll just, here, you know what? I'm not here. Is 6331 prime? No, it's not prime. Okay, wait. Yeah, okay, I don't need to... Okay, hold on. Factors of 6331. Okay, 13 and 487. That's it. So, unless... what was the number again? I already forgot. 1261. Okay, so 13 and 487. Oh my god, they both divide by 13. Wow, that's amazing. Okay, that's actually like really impressive. Okay, so 1261 divided by 13 is 97. So, and then 331 divided by 13. Oh wow, that's actually like really cool. 487. It's better, I guess. So yeah, that's kind of neat. They're both divisible by 13. I'm pretty sure that's okay. So let's just make sure. Factors of 4. What was it? 487. 87. Okay, it's prime and then 97. Prime. Okay, yeah, they're both prime. Okay, so there's your total resistance. Oh boy, this is gonna be fun circuit question. All right, I'm gonna keep it that way. I'm determined. Okay, well, therefore the total current. So we have 10 equals I times 487 divided by 97. So, I 970 divided by 487. Probably not prime. Or probably is still. Well, 970 is not prime, but like it's not going to simplify. Oh, that's so close to 2. Oh man. Oh, you have to just ruin it for me. Is what is 974? Yeah. Okay. Oh, it's so close. I'm gonna keep it. I'm gonna struggle. I believe in the struggle. At this point though, I should probably have like actually, you know what? I probably shouldn't. I should have. Okay, so I got like 1.2, right? Or no, 1.99. So what this means is that this should say like 1.99. Yeah. Okay. So I got that right. So it seems that this situation was not a problem. Okay. I should probably just say screw it and just do the it's decimals because at this point it's getting ridiculous. Okay, because wait, 487. So that's 5.02. Yeah, you know what? I'll just fine. I normally like wouldn't really want to do this, but since like it does this only goes to 2 decimal places, so it's like I want to, be able to figure that out easily without converting everything. So, okay, so now we have to go and figure out voltages and currents. So, the first main thing we have is we have, okay, we have 1 is, R1 is in series with the battery. So this means that it follows the series rules. So the currents are equal. So I1 equals I total. I should clarify this is total. Okay. Equals 1.99 amps. Okay, so we can put that in. Okay. So therefore, well, the voltage is also just 1.99 volts because it's, just V equals IR, right? So V1 equals I1 R1. So we have 1.99 times 1 equals 1. Volts. Okay, so we have that. So, but for voltage more specifically, is that we have the total, and then we have V1, and then we have everything else. So what this means is that V total equals V1 plus V 2, 3, 4, 5, 6, 7, 8. So that means we have 10 equals 1.99 plus V 2, 3, 4, 5, 6, 7. So V 2, 3, 4, 5, 6, 7. I know I forgot the capitalization. Hold on a second. would be 8.01 volts. It's so annoying. It's so close to 2. Oh man, if it was just 2, it'd be so much nicer, but it's not. Okay. Okay, so that's voltage for that. This also means that the well, hold on. Okay, so from there we have 2 main branches. We have the top branch and the bottom branch are in parallel. So parallel rule says that things must be the same. So for voltage, so V 2, 3, 4, 5, 6, 7, 8 should equal the voltage for 2, 3, 4, which should equal the voltage for 5, 6, 7, 8. Okay. It equals 8.01 volts. So, yeah. Now, therefore, the currents. Well, wait, hold on. Let's hold on the currents. We don't need those yet. Well, okay. So what do we have? Total current's 1.99. So that means the current leaving here is 1.99, right? So let's try not to get everything else. Yeah, it's 1.99. So that means that the current from this total top part together must plus the current from this total bottom part together must equal 1.99. So I1 equals I234 plus I 5, 6, 7, 8. Why did I put a 4 there? Because I'm dumb, that's why. Equals 1.99. Okay, so we have currents and voltages. Okay, so let's look at these. So now in series okay, so what's in series here? So 8, 7, and then 5 and 6 together are in series. And again, for currents, when they're in series, they're equal. So this means that I 5, 6, 7, 8 equals I 5, 6 equals I 7 equals I 8. So, and this all equals what? Oh, it equals 1.99 minus that. That's annoying. Okay, equals 9. We don't know what that is yet. But I234, it's a similar situation because this one's in series, so it's going to equal I23 equals I4. 1.99 minus I. Okay, so we have to come back to that probably. Okay, so voltage is. I feel like I'm making this hard because I can't just like. Oh, well, okay, I can do something easier. Is that I know I can use Ohm's law. I know what V234 and V5678 are. That's 8.01. So what I can do is I can say V234 equals I234 times R234. Now I have so 8.01 equals I234 times, and we have this up here. So we want R234 is 26 fifths. Make sure it's 234. Okay, so 8.01. Oops. 1.54. All right, 1.54. Okay, so I234 is 1.54, and I234 equals I23 and equals. Okay, so equals I23 equals I4. Okay, so we have I4, so that's 1.54. Which also means we can get V4. So 1.54 times R4, which was just 4. 6.16, okay. Okay. Now what are we at? Okay. So where can we use V4 to our advantage? Well, V234 equals V23 plus V4 because it's the velocity. No, not velocity. The voltages are summative in series. So, yeah. Oh wait, so let me check. It was 1.54. Yeah. And then here, let me put this up as well. Out of the way. I'm gonna usually forget which order is which here because I usually do that, but 6.16. All right, sweet. Okay, so those are correct. So this means this voltage plus these two voltages needs to equal the total voltage for this whole thing. So when we have that, right? Because we have V234. Don't we have that? Yeah, that's 8.01. Okay, so it's 8.01 equals V23 minus 6.16. So let me double make sure I didn't stop recording. Okay, I'm still going. Okay. Just making sure because I remember the whole thing with the tilde thing that stopped it. So and I didn't press the shifted part of it. Whatever. Okay. So V23, oops, 23 equals just 8.01 minus 6.16, so 1.5. Okay. However, V2 and 3 are parallel, so their voltages have to be equal. So this just equals V2, which equals V3. All right. So 1.85, 1.85. All right. So now we can divide to solve for I2 and I3. Okay, so we have 1.85 equals 2. So I2 equals 0.925. Okay, and I3 is going to be 0. Oh, be lame, it's 0.62. Okay. Okay. And then we're done with the top row, or the top part. Okay, so let me check this again. So 0.62. All right, and then it should be 0.93, probably rounding. 0.92, okay, rounding. And then that means this should be both 1.85. 1.85. 1.85. Okay, that part is done. So, oh, well, I know, okay, hold on. So I know I4. Where's I4? I4 is up here, 1.54. So I know I4, and I know that I4 equals I234. So I have that. So I have I234, and I know that I234 plus I5678 equals 1.98. So basically, yeah, I can do this now. Okay, so, let me go. Okay, so I56 equals I7 equals I8 equals 1.99 minus I234. Except I have I234. I234 is 1.54. So 0.45, yeah, okay. So I7 and I8 are 0.45. stupid thing. And I can now solve for V7 and V8. So V7 equals I7 times R7, so that's 0.45 times 7, which is 0.15. 8 equals I8 times R8 equals, which is what, like 0.6? Yeah. Okay, 3.15 and 3.6. And then all we need left are 5 and 6. Okay, so we have I5, 6. We have... Okay, and then we can do this for... Okay, then we have voltage. So the voltages should all be additive, because now all these are in series. So, V5, 6, 7, 8 should equal V5, 6 plus V7 plus V8. And we have V6, 5, 6, 7, 8. It's 8.01. So we have 8.01 equals V5, 6 plus 3.15 plus 3.6. So 8.01 minus 3.15 minus 3.6. Okay, 1.26. And since those are in parallel, that means these are equal. All right. Okay, so we're basically done here. And then we just got to divide out to get the i's. So we have 1.26 equals I5 times 5. So I5 equals... Oh, I already had it. Well, whatever. 0.25A. (1.26) I6 times 6. Wouldn't this be just like 0.2? (0.21), okay. Oh, right, yeah, okay. And we can then check. All right, so let's double check. Let's see. So this should be 0.25, 0.21, and then what were the currents? It was 0.45 for both of these. 5.45, yep. And then voltages were 1.26, 1.26, 0.23, 3. That's odd. Did I just math wrong? Or maybe it could be a rounding thing. Oh, is it because this is 3.2? Let's see, wait. 3.16, no, that's 3.16. I think this is just rounding, because then this should be 3.6. Well, this would be negative right now, but 3.61. Okay, I think it's a rounding thing. Yeah, because that was 0.61, so that's 1 off. And then 0.16, so that's 0.02 off. And then, yeah, it's a rounding issue. Because, okay, well, here we can check. So what's this to this would be 8.01. Yeah, it's a rounding issue. That's what that is. So, okay, that's... And then this would also be 8.01. Yup. And then that would leave this at... I don't know if... Did I ever check this? I don't remember. 1.99, because that adds up to 10, which is what it would be. Well, 10 here, really, but... Yeah, okay, so we solved that. We have all the numbers. That took a while. That's what you get when you just make this kind of out of the blue. I'm disappointed. It was like so close to being like if 5-2, it was so close to being like perfect. It was just random chance. Like, oh man. Um, oh well. Then that would have made things nice and simple, but they weren't. So well. Um, yeah. Oh well. Well, okay. There's your circuit question as an example. Again, you can find definitely the circuit worksheet that we went over. Spring break. That can have lots of examples of that. So yeah. This is probably like about the hardest of something that I would give you, like the absolute hardest. Um, but it'd probably be at least a bit easier than this. But yeah, for example, like the question on the electricity test that was like, here's a circuit, what's the total resistance, and then from there it was like, do these resistors have like the same current? Why or why not? Or do these have the same voltage? Why or why not? That kind of question. Could be like a circuit like that, but I would say like actually find what the currents and voltages are, and not just like are they the same. So yeah. Um, okay, I guess we're ready to go to the astronomy stuff, which is kind of a new thing. Kind of see what we got. So that's not an 8. Okay, so there's only a couple real questions we could go on here, and there's so you have uh questions about like the spectral class of the star. Um, you have transit graph questions, and you have relativity questions. Those are kind of your main things in terms of like a mathy kind of question, which is what you should expect. So let me show you what's on the formula sheet for this, because you might not know what to expect. So I give you, here's the star classification. There's the order, right? O, B, A, F, G, K, M. And then I tell you what the Roman numerals are, right? So kind of your giants, your super giants. Again, this 2 is sort of your halfway between point. 4 is sort of your halfway between 3 and 5, and then 5 is the main sequence. I give you, here's your luminosity of a star equation. So the brightness of the star is 4 pi times the radius of the star squared times the sigma times t to the temperature to the fourth. And here's what the sigma is. Here's the equilibrium temperature equation. This is going to be a part of like the transit graph stuff. So yeah, you have temperature of the star times the square root of radius of the star divided by 2d. Here's your light blocked from a transit. So basically this is the amount of light that's blocked equals, as a decimal, equals the radius of the planet squared divided by radius of the star squared. And then you have your d. I should change this to like, it's your a. It's your semi-major axis. Oops, wait. In AU, I'll do that. And then T is that, and yeah. So is that going to equal your the orbit the time in years to orbit squared, and then that's actually times the m in solar masses. So I'll show you how that works, and then yeah. So these can all be kind of related to each other. I should probably change this because I use like r orbit. You know what? I'm actually gonna put ASM, your semi-meter axis, for that. Just to clarify that this number is the same as this number. It's just that in here it's measured in the meters, the standard unit, whereas here it's specifically measured in AU. So that's sort of the clarification of that. Oh, do I have an AU? Oh, I do. Okay, so I have the conversion between AU and meters. Okay. Then I tell you a bunch of numbers for the sun. So the mass of the sun in kilograms, the radius of the sun in meters, the brightness of the sun in watts, and then also the sun's surface temperature. This is if you're converting between like solar mass, solar radius, and that kind of stuff. Yeah. And then there's your Drake equation if you need to do a thing for that, which could come up, I guess. And then here's your relativity stuff. Again, your speed of light, which we've done with a lot. For the Lorentz factor, this is again your gamma equals this. This is I just took this equation and basically reworked it to solve for v. So if you are given gamma and you're asked to solve for the velocity, you could use this to work backwards and figure out what the velocity is just straight by plugging into that if you want. So this is not like a new formula. It's just this reworked to solve for v. And then clarifying that L, M, and T are values measured at the moving frame. And oh, I just didn't give you the Lorentz equations. That's stupid. Why didn't I do that? You know what? You don't need this. You know what? Screw that. You don't need to use that. So I need the space though. That's the problem. Okay, how much space does this take up if I put this in? So L equals L prime equals L divided by gamma. M prime equals M times gamma. And T prime equals T times gamma. Yeah, that's... You know what? I know what I'm going to do. It's going to look really ugly, but I have a plan. Let's see. Oh, because of the... Okay. Okay. I think this is going to work. That looks pretty good. Yeah, that looks good enough. So we have speed of light is that. The Lorentz factor is this equation here. And then you have your how your length, mass, and time change, and then I clarify which length is which mass is which. Okay, that works. That's good. Okay, I'm satisfied with that. So, the luminosity, or no, not luminosity, the stellar classification, that's going to be a question like, let me pull up thing. Did I save the blank document? No, because this is... Oh, this is blank. Okay. So, for example, it could be like, just asking kind of where a star is. For example, I might have like... I'm not going to have you like plot a thing itself and turn in an image or whatever, but it could be like, here's a bunch of stars. Like, there's a star here, and a star here. Like, what are their classifications, right? So, for example, if there's a star here that's in the middle of the G column, so if it's in the middle of the G column, that means, well, it's a G, and then the number, remember, is the subdivision within the G. So if it's in the middle, it's probably a G5. And then if it's in this giant section, it's going to be a G5 3. Okay, Roman numeral 3. If something's like down here, then it could be like a K8 5 or something, Roman numeral 5. Up here would be like a B1 Roman numeral 5. Something like here, like this one, would be, I don't know, like an A6 or A7. It's up in the super chest. That'd be A6 or A7 Roman numeral 1. A Roman numeral 2 would be something like maybe some of these would be Roman numeral 2s, and then Roman numeral 4s would be like that one is kind of like up a bit, like that one maybe Roman 4, maybe that one. I don't know, that one I'm not sure about because like that's also kind of like just in line with the 2s. Because the thing is, like, all of these lines sort of like they're not straight, right? The V is curves up this way, and the Roman numeral 4 also curves up this way. Roman numeral 3 sort of curves up this way, and Roman numeral 2 sort of goes like that, and then Roman numeral 1. So like they all kind of converge up here, so it's really hard to tell. I'm not going to give you something that's like way up here because it's too hard to tell if what the Roman numeral is. So, but yeah, there's going to be some sort of question like that. That'll probably be linked to a transit question, where I'll say like, "Oh, you have these stars or whatever, blah blah blah," and like tell me which one their classification is, and then I'll say, "Okay, let's take this star. It's mass or radius or blah. It has a planet that does this based on a transit graph, blah blah," and go from there. So let's pull up the transit graph thing and let's do an example of this. Let's see, what do I want to pick? This is like always defaulted. I never want that out. Okay, let's do all the way down. Okay, pick a random one to do. Eight. Actually, let's not do 8. Let's do rows for a second. You want to do a double? Nah, it's not do a double. I feel like I did 10. Let's do 7. I'm pretty sure I didn't do 7. Okay, this is gonna be a big planet. So Kepler 7b. So we need star data. That means for Kepler 7. And I'll just like give you I'll give you a graph for it, so you don't have to worry about that. So Okay, so Kepler 7, E0. Interesting. Okay. All right. Okay. Okay. Here's the numbers we have. So, oops, where here? Okay. So, transit of Kepler 7. Well, actually, here let's look at the star. So, what does it say it was? That it was a G0. Huh? It doesn't have a Roman numeral. That's odd. Yeah, that's kind of odd that it doesn't have a Roman numeral. Huh? I don't know. I wonder why. Um, okay. Well, anyway. So, the mass. We have the star's mass 1.347 times the mass of the sun. So 1.347 is 1.347. Okay. The radius of the star is 1.843 times the radius of the sun. And the temperature of the star is, what was it? 5933 Kelvin. Okay. So we have the numbers for the star, and then let's look at the transit data. Okay, so here's our transit data. So, okay. Using transit graph, find the, let's see, the radius of the planet, the orbital radius of the planet, and the equilibrium temperature. Let's do that. Okay. So, for the radius of the planet, in order to find that for transit, that's going to be using this graph, or this equation here. R planet squared divided by R star squared. Okay. Now, looking at the graph, what's delta F going to be? Almost 2.6. Pretty much is 2.6. It's not quite. But you know what? I'm going to be lazy and say 2.6. So again, but it's 2.6%. Okay. So, it's 2.6%, which means it's 0.026. Okay, right, so don't forget that. No, we want to find RS, but we want to find RP, the radius of the planet. R star, it's 1.843 times the radius of the sun, which is 6.955 times 10 to the 8. So we need to get this in meters. So where's my calculator? There it is. 1.843 times 6.955. Okay, so it's going to be 1.2818 times 10 to the 9 meters. Okay, so we have 0.026 equals the radius of the planet squared divided by 1.2818 times 10 to the 9 squared. So let's square this. You get... What? Oh, because I didn't... Okay, hold on. So this times... Okay, that square this now. Okay, 1.643 times 10 to the 18. All right, so now you're going to multiply this over. So times 0.026. Oh boy. I'll just write 4.619. Okay, so the radius of the planet is square root of this. I'll write up to here. Nope. I'll include the comma. Meters. And here, I should specify, I often want this in Earth radii, and I give you, okay, so the formula sheet, I give you all these numbers for the sun. The numbers for the Earth, I mean, you could look it up, but it's at the top here. So the mass and the radius of the Earth are up here. So whenever you want to solve for like the radius of the planet in Earth radii, you take whatever number you get there and then divide it by this number. So, oops. We're going to divide by 6371. Okay, so it's 32.44 times the radius of the Earth. It's like Jupiter-sized, I think. Actually, it's bigger than Jupiter. Okay. I'll clarify which kind of radius I want, so don't, like, you know, on the test, don't think like, oh, how am I going to know or whatever. So yeah, okay, so we have that. Okay, next up we want the orbital radius of the planet. So that's going to be figured out from this. Where is it? Here. Okay, orbital radius, the semi-major axis, we're using those interchangeably. Okay, so don't worry about that. So we have that A m cubed equals t in years squared times m sun. Basically, the mass of the star in solar mass units. So, now we want t. Okay, so t in years. Let's look at the graph here. So this lines up. Okay, it's not perfectly on the lines, but this is almost, it's a little bit more than 3, and it goes to 8, then a little bit less than 13, then a bit less than 18, then less than 23. So this is a bit less than 5. What do we want to say? 5.8? 5.9? Comparing this to this, it's like maybe about half a day's difference. So half a day's difference over 4 rotations would be I'm gonna say 5.8. If you want to say 5.9, then it'll be fine. But okay, well, hold on. I mean, get rid of the negative or the equal. So t in years, it's going to be 5.8 days divided by 365 days. Or no, not 5. It's 4.8. Sorry, it's less than 5. Okay, almost got this completely wrong. Okay, 4. No, wait. Okay, 4.8 divided by 365. Okay, 0.01315. And then m, what did I just do? Okay. M star, we have that already, that's 1.347. Oh no, it's off. Okay, just because the tab breaks it, so okay, there, that breaks it. Okay, that's good. So then we have all the numbers we need. So we have, so t squared in years, so 0.01315 squared times the mass of 1.347. Okay. So we're going to square this. Okay. 17294 times 1.347. Okay, so we have A cubed equals 23295. So now we want cubed root. Okay, 0.06153, and this is an AU. Zero 0.6153. To get this in meters, we're going to multiply by the number that I give you in the formula sheet here. So we're going to need this in meters for the equilibrium temperature anyway. And again, I would clarify, so don't worry about this again. So to get this in meters, we're going to multiply 0.496, 10, 11, Okay. I'll do 9.205 times 10 to the 9. Yes. Okay. Last equilibrium temperature. Wait, no. A. Okay. So we have T star. That's temperature of the star, 5933. We have R star. Again, this is in meters, so we're going to have to use this number here. 1.2818. No. And then ASM, we just got that right up here. So that's very close. This plant's going to be smoking. Okay. Oh, jeez. All right. Okay, so we have 5933. And then the radius of the star, which is 1.2 times 10 to the 9, divided by 2 times 9.205 times 10 to the 9. Okay. Multiply this by 2 first. Okay, so that's 1.841. And all right. Six, 9. And then I gotta flip it though, so it's this number doesn't round real well. Pooey. I'll write that, but I'm not gonna actually. Okay. Okay, so that number is going to be that inside of the square root. Then we square root it, and these numbers are still annoying. Well, that's actually not terrible. Oops, 933 times that number. And our equilibrium temperature of this planet is, oh, yeah, only 1,556, no, 1,565.5 Kelvin. Which, just to do it, let's find Celsius is 1292. And then Fahrenheit is 2355. So, yeah. That's tolerable. Yeah. Hey, actually, you know what? Let's check our numbers versus the actual numbers of the planet here, because we can figure out what that is. So, here we have. Let's see, the AU looks right, because, yeah, 0.06 something AU. What did we get? 0.061, 0.062, that's pretty dang close. Orbital period. Okay, yeah, 4.88, so it should be 4.9, but whatever. Or 4.09. Or 4.9. Okay, do we have radius? That's 1.4 times mass of Jupiter, which that's probably about what it is. Temperature. Wait, 1540? Is that like what I had? Oh, that's so close. Oh, look at that. Actual temperature 1540, and I got 1566. That's close. That's good. I'm proud of that. So, yeah. So something like this, again, this is probably the hardest kind of thing you would do for this sort of stuff. Like I think this kind of problem is sort of probably the hardest that you would have. I mean, relativity again, like mathematically, is not super difficult. It's just kind of weird. So okay, let's do a relativity thing. Let's say, Ooh, I know. Hold on. Fastest spinning neutron star. Okay, so yeah, so it's that many times a second. So if you were standing, hold on. Okay, so let's do some math here. I want to know if you're standing on this. Okay, 16-kilometer radius. Okay, so it rotates that many times. That means it goes 2 pi r of this radius every this seconds. So these things are stupid fast. So okay, so we have 2 times pi times 16. It says less than 16, but I'll just use 16 kilometers. Okay, so that's your circumference. And you do that every this many seconds. So we're therefore going to divide this by 139595482. Okay, that's our speed. Do I want to go? Yeah, you know what? Screw it. Let's go that specific. Let's say, well, let's round it to 16. But you know what? Let's say that. Okay. So, this is a relativity question. You're standing, and this would be your equatorial. If you're standing on the equator, on the equator of a neutron star that is spinning at I said change to 6 meters per second. Somehow you're not dead. Don't worry about it. Find your Lorentz factor and let's start with that. Okay, find the Lorentz factor. So the Lorentz factor is 1 over square root of 1 minus v squared over c squared. Okay, so we have 1 over square root of 1 minus 72015,916 squared divided by 300,000 squared. Oh boy. Okay, so we want to square this bad boy. Ew. Okay, so I'll do 5.1863. That's times 10 to the 3, 6, 9, 12, 15. 15? Oh, why you gotta be like that? Okay. I'm losing my mind. Okay. So we're at, what was it? 5.1863. Man, that's like not much of a difference. Because I think it wasn't this like it literally spins like 24% the speed of light or something ridiculous. Yeah, it's equated to spinning approximately 24% the speed of light. So yeah. Okay, so we're gonna divide this by 6, 7, 8, 9, 10, 11, 12, 13, 15, 16. Okay. I'm gonna go all the way to here just because I can. Because I have the ability and the authority. And who's gonna stop me? No one's gonna tell me no. 1 minus that. Oh man, the thing didn't thing. Oh, it's there. Okay, there. That worked. Okay, so 1 minus this. Okay, so that would be that. Gonna be quite a number. Okay, then square root it. And let's go to here. Oops, I pressed the wrong thing. Oh. Which means our Lorentz factor is surprisingly not as much as I thought it would be, to be honest. Let's round it here, I guess. Okay, there's your Lorentz factor. That's like kind of disappointing, honestly. I expected it to be more. But again, this is you're moving at freaking 20, like a quarter of the speed of light, and you're barely like 3% over what you normally are. So let's say your rest mass. Oh, let's say your cone mass is 80 kilograms. Your length is 0.15 meters, and you're on the neutron star for, let's say, 1 day. What mass, length, and time does someone outside of the neutron star observe? Okay, so I've given you numbers for what you measure while you were there, and I'm asking you, what are you finding? I'm asking you what values does someone outside of the moving thing observe. So because of that, you are solving for the prime values, not the. I'm giving you the standard values. You're solving for the prime values. Again, always double check, because it could be a question that could ask the other way around. So let's start with the mass. So we have 80 times 1.03012. Okay. Now we get to 82.4 basically. So you're an extra 2.4 kilograms heavier. Your length. What do we add? 0.15 divided by 1.0. So then we're at 0.14. So you're about half a centimeter smaller. Which, I mean, that's not, not imperceptible. In now time. Now I'm going to be fancy. And I'm going to use the number of seconds in a day. Just so I can get this more accurately. And I know that this would be 60 times 60 times 24. And I know that that's 86,400. But again, you of course could calculate that yourself. 03012. If you just put in 1 day and then you get, this, then I would probably want you to convert to like seconds or something. So let's see what we get for seconds. So let me flip this around and yeah, it's the right number. Okay, so then times 86,400. 89,002. Interesting. So how much? Which is a difference of 2,602 or 43 minutes and 22 seconds. Interesting. Interesting. Okay. There you go. There's your examples of stuff. The circuit problem probably took the vast majority of time for that, but those take time. So these are the types of questions you should expect. Of course, the scenario could be a bit different. Numbers could be a bit different. Again, definitely for the relativity, check to be very careful if the numbers that I give you are the normal numbers or the prime numbers, and which ones are you solving for. That's to be very careful of that. The transit thing, the main thing is just keeping track of all the numbers because they're not the greatest. And then also being sure to, like, for example, you have to use this number here. It has to be the meters number. It can't be the AU number. That's something to be careful of, and some other stuff like that. Circuit thing, of course, you just have to be careful about in general, and then the have all the stuff about the fields and things that you should know how to deal with those. So yeah, I guess that's that, and we've almost filled out another page of this. How long is this document? 58 pages. Oh, good lord. Okay. Yeah, that's that, I guess. So tomorrow, I'll give you the link to the final. And I'll also give you the formula sheet. I mean, you've seen it now already, but I'll give you the file. Um, I guess that's basically it. You'll have, of course, all of next week to work on it. Um, and of course, turn it in by the well. I guess just turn it in by the last day of school, which would be June 3rd, 2 Wednesdays from now. Um, I know senior graduation is before that, so I guess seniors turn it in by the Friday. Um, but honestly, like, you know, as you probably figured out in terms of grades, it's that it's doesn't really matter right now. um, but I still want people to do it, to see how things work and make sure they kind of know what they're doing. Um, and there will be a big semester-wide Kahoot on Tuesday. That's sort of your last kind of assignment of things. If there is any sort of late work you missed for like AP tests or whatever, then yeah, you could turn that in um, as well, kind of throughout next week. So yeah. Um, but this is the last video that's going to be posted for the year. Um, we'll see what happens next year. I have no freaking clue. Um, yeah. And yeah, of course, any seniors who are going to be graduating, good luck with the world. um, I mean, same for, we're all in the same situation. It's not like, this is not going to be like resolved, in a month, right? It's just not. Um, there's no way that like next academic year is going to be normal. Even if you're going to college, it's definitely not going to be normal. Um, or just you still have more years to go. It's not going to be normal. Um, it will not be normal until we have like widespread vaccine usage. Um, so even after we get the vaccine, we have to actually have people get the vaccine, which is going to take a while. So yeah, and I remember reading a quote from someone. I don't remember what it was. Probably just some random Twitter or Reddit thing that was like, I always imagined what it'd be like to be living in like during some big like historical event, but like now that it's happening, like it sucks. It's like, yeah, things are big and important because they cause big changes and unexpected things happen, and we don't, and society kind of has to figure out what to do about it, you know, and that takes a while to figure that stuff out. So, yeah, I mean, again, the Discord thing is going to be open. So I'm not. It's not like I'm gonna close it like June 3rd or whatever, the last day of school. I'll leave it open, um, for whatever. I might just stream random crap on Twitch at some point over the summer. I don't know what I'm doing over the summer, um, but we'll find out. So yeah, I guess that's what we got for that. Of course, but again, any for the final, any sort of questions or help for anything, you can of course message me, email me, whatever. Um, I will say I might be kind of slow on responding to emails because for some reason my phone like doesn't give me notifications if I have like emails sent like to my the emptyusd.net Gmail account. I don't know why. Like I get the emails, but it doesn't like give me a notification like, "Hey, you got an email." I have to like go manually look in and see if I got it, which like I sometimes forget to do. So and I saw some people who like asked me like a thing like a few weeks ago, but it was like by the time I looked at it, it was kind of like the question didn't really matter anymore. So I was like, oh, sorry. um, but yeah, so hopefully that should be okay. And yeah, so anyway, this video's probably gone on way too long already, so I need to stop this. So, this is last video, and it's ending.